Hello, my name is Leslie Dawn Hunt. I am in Topics in Data Science, and this is my final project. The title is Time Series Analysis of Monthly Highest Temperatures and Average Humidity in South Georgia from 2018 to 2024. For an executive summary, the objective of this project was to explore time series data of monthly highest temperatures and average humidity percentages in South Georgia. Specifically, the data collected was from July of 2018 to June of 2024, and all of the data was monthly. So from July, August, September, and so forth. The methods that I used to analyze the data, it is the seasonal decomposition using STL and the ARIMA forecasting, and I did this all in Python. Specifically for the ARIMA method, I had to add another variable being humidity, so I used ARIMEX to use, basically it's ARIMA with another variable added on. Some key insights, we're going to be looking at the decomposition. It identified significant seasonal and trend components. That's what it will be doing. And the ARIMA model will forecast future values accurately. For methodology, data resources and collection, the source was from Weather Underground, wonderground.com. The specific location that the data was reported from was Southwest Georgia Regional Airport Station in Albany, Georgia. For data collection, the specific process, I manually went through each month and found the average humidity percentage and the highest temperature recorded for that month. And I put all of that data into a CSV file. And of course, each of these data points range from July of 2018 to June of 2024. And for the focus, we're going to be looking at hottest temperatures of each month and how they correspond with average humidity. So we'll be looking at the trends and possible patterns. For data cleaning and preparation, of course, I use Python. I use a pandas package. For date parsing, I converted the date column to date time format. And deviations, we calculated the deviations from the mean for temperature and humidity for seasonal decomposition. For the algorithms and models that we use, I'll be doing seasonal decomposition using STL, where we will be breaking it down into three components, which is seasonal, trend, and residual, and we will be using a period of 12. ARIMA forecasting, the parameters found were P equals 12, D equals 1, and Q equals 0. And we forecasted we forecasted future values for 30 months. Data analysis, we will be seeing graphs, ACF plots, and trend lines, and we'll be evaluating all these. For changes in the data collection, the initial plan was to analyze the highest temperature and average precipitation at a monthly rate, but through observation, precipitation was reported as 0 on all of the hottest days, or at least for the majority of the reports, it was a lot of zeros. So I decided to change this. And I decided to go with humidity since the data looked more interesting and there was more to work with. And this does make sense with logic and how on the hottest days there will be less rain. So at the start of our data exploration and analysis, I wanted to just see like a simple layout of the relationship between the two values according to the time recorded. So I graphed both the highest temperature data and the average humidity percentages. And you can see by this by this plot, that they really do have an inverse relationship. So I'm guessing right here starts the summer of June 2018 about there's high temperatures and low humidity. And as it goes into the winter towards the end of 2018 and beginning of 2019, temperatures are low and humidity is high. And you can see that as you go around. This could be considered the summer months, so the summer of 2019, right? The summer is low humidity, high temperatures. And then you can see that it oscillates like this all throughout. So it has an inverse relationship. Then I went into doing the ACF autocorrelation function plot. And when we look at this, you can see that there's a peak where 12 is. So we can assume that our seasonal component, or the period of the seasonal component, will be 12. And that's what we will work with in our analysis. P equals 12. All right, for the seasonal decomposition, I had to do it for both highest temperature and average humidity. Seasonal decomposition, you can observe this deviation, trend, seasonal, residual, and also for average humidity, you can observe them as well. You can see, like, in these first two lines, you can see how they are still inverse. So, like, at the start, it goes up, at the start, it goes down, continuously that way. The trend lines, looks like they are still inverse. It goes up, oscillates. Here it goes down and does the same thing. And really the seasonal component is pretty interesting because you can see at the tops, the peaks, right? This would probably be more so like the summer of 2018, right? The winter starting of the end of 2018, starting of June, or starting of 2019. So summer, right? High temperatures, winter, low temperatures. And you can see, like, at the bottoms, those temperatures every year, the highest temperature reported seems to continuously go slightly more up and up. And for the peaks as well, they seem to slightly go more up and up as the years go by. See how this peaks and this peaks? It's like slowly going upwards. And for humidity, it seems that these averages at the top are going down, and then these at the bottom are going up. So it's kind of like converging. And then this is just all of those components put onto one plot for each. So for highest temperature, you can see the trend line on top of the seasonal component and how it fluctuates. Here's humidity. You can still see, like in the original data, you can see how the lowest humidity is starting to rise. And the same thing with temperature. The highest temperatures, you could say, recorded in the winter seasons are increasing as the years go by. For AREMA forecasting, we had to do the stationary test to determine if the original data was stationary or not. We used ADF tests, and that gave us two statistics. It gave us the p-value, and it gave us an ADF statistic. So for the p-value, that determines if it's below 0.05, it is stationary. If it's above 0.05, then it is non-stationary. So the original data was non-stationary. We got a value of above 0.05 for p-value. And then we did first order differencing after we determined that to see if it was stationary. And once that was done, we got a p-value below 0.05. So because first order differencing was stationary, we can assume that perimeter for D is equal to 1. According to the plot that we did here for ACF first order differencing, you can see that there's a peak at 12. So that stays consistent. P will be 12. And then after we did that, we need to do AIC scores using D equals 1 and P equals 12. This will help us find Q. So according to these scores, this was my output. The lowest AIC score is what we will determine as Q. So this will be 0. Q equals 0. And then once we do that, we can use that model and calculate our forecast. And I decided to do, in the future, 30 months with an 80% confidence interval. And you can see it's pretty consistent. The model is accurate. It shows a fluctuating pattern. So for results and discussion, seasonal decomposition. Findings, I put the graphs here again to just visualize it. There is a clear seasonal pattern. There are annual fluctuations, of course. For trends, I see a gradual increase in highest temperatures and the average humidity each year. Maybe for humidity, it's harder to see at the top, but at the bottom, you can see like for the winter months or the summer months. So the summer has lower humidity. It's like slowly increasing. I think this could become more accurate if I were to get more data, maybe collect from 2000 to 2024 in order to see better forecasting also. But for now, I think I see gradual increases in both given the 6 year period. And the relationship, of course, between the two values, highest temperature and average humidity, it is inverse. They're inverse of each other. When it's the highest temperature in the summer, humidity is very low. In the winter, its highest temperatures, of course, has higher levels of humidity. For remote forecasting, we had reliable predictions with the confidence intervals, and for the implications, rising temperatures correlate with lower humidity during the hottest months. For strengths and weaknesses in my models, I would say strength would be accurate insights into the temperature patterns. The future forecasts were pretty accurate. Weaknesses, the non-stationary values, maybe tuning with the parameters like P, Q, and D. The limited data, I only did 6 years to be easier for data collection, but future work would be to get a larger data set and maybe incorporate additional variables that would also affect high temperatures. Potential biases, um, the measurement errors, maybe external factors like precipitation, wind patterns. This goes back to like adding additional variables that could potentially impact temperature without, like, we don't see that in this data, but other stuff might impact it as well. Data collection, I did do the manual extraction. There could be a chance I have a point something off. Also, when it's reported at the station, there might be a mishap in reporting. And also another note I wanted to make for potential biases was when I collected this data, I set all of it to the first of the month to have it evenly distributed, but I didn't take the specific date that the highest temperature was recorded for that month. So maybe going back and recording the specific date for those recordings would give a variation of plots, a little bit different, but we can only tell if we did that. For areas of further exploration, for enhancements, of course, add variables, maybe to see different relationships, use different models, maybe use something else than their ARIMA model for better forecasting, and of course, expand the data. I was also thinking another would be for areas for further exploration. It would be interesting to maybe do the same kind of project with a different area and compare those plots. So, like, instead of Albany, Georgia, find maybe somewhere in the west or in the north and compare their highest temperatures and how they fluctuate. Maybe are they going upwards? Is the humidity as high? Is it lower? It would be interesting to see that data for different areas and locations in the U.S. So as a conclusion, my analysis was a success. Everything was analyzed correctly and forecasted for the next 30 months. Insights that I saw were seasonal and trend components, accurate forecasts, and of course, this helped give some valuable predictions for the future, better understanding for climate trends that might be coming our way. And key takeaways as a final note, we had an inverse relationship between highest temperature and average humidity. There was a gradual increase between, both highest temperatures recorded every season and the average humidity percentages that were recorded on that relative day. So it is a very small increase that I noticed, but I mean, it can be noted. And of course, trends were all consistent and observed throughout the period. And thank you for coming to my presentation.